Now, let's discuss solution to differential equations. A function u of x of y is a solution to a differential equation if it satisfies the differential equation, i.e., if we substitute u prime, u double prime, u triple prime, all the way to un into the differential equation, then we get the desired expression in the differential equation. There are two types of solutions to a differential equation. It can either be general solution or particular solution. A solution is called general if it has unspecified arbitrary constants. A particular solution is one in which the arbitrary constants are specified. Normally, we get a particular solution from a general solution by using the initial conditions. If the initial conditions are all specified at the same point of the independent variable, this constitutes an initial value problem. If the initial conditions are given at more than one point of the independent variable, then this constitutes a boundary value problem. Let's take some few examples. Suppose we have y equals to c1 sine x plus c2x. This is a general solution because the arbitrary constants c1 and c2 are unspecified. Suppose c1 equals to 3 and c2 equals to 5. Then we can write y as 3 sine x plus 5x. This is a particular solution because the arbitrary constants c1 and c2 are specified. Now, suppose we have y double prime plus y prime minus 2y equals to 0. Then we have y of 0 equals to 2. And you have y prime 0 equals to 7. We need to understand that this value always represents x and this one represents y. Similarly, 7 represents y and 0 represents x. Now, since we have y and y prime, then this constitutes an initial value problem. Other example, suppose we have the same y double prime plus y prime minus 2y equals to 0. But this case we have y of 0 equals to 2 and y of 3 equals to 8. Remember, 8 represents y and 3 represents x. Similarly, 2 represent y and 0 represent x. Since we have y and y, then this constitutes a boundary value problem. Okay. Example 1. Show that y equals to c exponential to 2x is a solution to the DE given by y prime equals to 2y. Now, for us to make the substitution into this differential equation, we need to differentiate this one once. So dy over dx will give us c exponential to the 2x. Then we differentiate the power of the exponent, that is, we get 2. So our y prime will be equal to 2c exponential to the 2x. Remember, from methods of differentiation, we learned that dy over dx of exponential to the x is simply given by exponential to the x times the derivative of x. Now, since we have y prime, we can substitute here. So we have 2c exponential to the 2x equals to 2 times y, but y is our original function given by c exponential to the 2x. The left hand side is equal to the right hand side. Therefore, y equals to c exponential 2x is indeed a solution to this differential equation. Example 2. Show that y equals to c1 sine x plus c2x is a solution to the differential equation given by 1 minus x cot x, y double prime minus x y prime plus y equals to 0. Now, this is the differential equation. In this differential equation, we have y prime and y double prime. Therefore, we are required to differentiate our solution twice. Let's start. Dy over dx will give us, when we differentiate sign, we get positive cosine. So we have c1 cos x. When we differentiate x, we get 1. 1 times c2 will have c2. Then d squared y over dx squared. When we differentiate cosine, we get negative of sine. So minus c1 sine x. The derivative of a constant is 0. So we have our y prime as well as our y double prime. Since we have these two, we can substitute them in our original differential equation. But remember, cot x is the same as cos x divided by sine x. Now, we have 1 minus x. Cot x is the same as cos x over sine x. Y double prime is given by minus c1 sine x minus c1 sine x minus x. Y prime is given by c1 cos x plus c2 plus y. Y is the original solution given by c1 sine x plus c2x. Now, let's expand this expression, and of course here it is equal to 0. Minus c1 sine x times 1 will give us minus c1 sine x minus c1 sine x times x cos x over sine x. Sine and sine will simplify, will cancel, giving us plus c1x cos x minus c1 cos x times x will give us x c1 cos x, then minus c2 times minus x will give us x c2 plus c1 sin x plus c2x equals to 0. Now, minus c1 sin x minus c1 sin x plus c1 sin x, we get 0. So these ones are cancelled. c1x cos x minus x c1 cos x, again these two will give us 0, so they're also cancelled. Minus x c2 plus c2x, again these two will also cancel, giving us 0 equals to 0. Therefore, y equals to c1 sin x plus c2x is indeed a solution to the differential equation given by 1 minus x cot x y double prime minus x y prime plus y equals to 0. Example 3. For what values of k is y equals to exponential kx is a solution to the differential equation given by y double prime minus 3y prime minus 4y equals to 0. Now, we need to get the first and second derivatives from this solution. dy over dx will give us exponential to the kx times the derivative of kx, which gives us k. So that is k exponential to the kx. d squared y over dx squared, it will give us k to the exponential kx times the derivative of kx, which gives us k. So that will be k squared exponential to the kx. Now, this one is our y double prime and this one is our y prime. Therefore, we can substitute them in our original differential equation. So we have k squared exponential to the kx minus 3 k exponential to the kx minus 4y, y is the original equation, exponential to the kx equals to 0. Now, as you can see here, exponential to the kx is a common term. Therefore, we can factor it out. Exponential to the kx, we have k squared minus 3k minus 4 equals to 0. Now, from this equation, exponential to the kx can never ever be equal to 0. Therefore, k squared minus 3k minus 4 equals to 0. Now, sum should give us minus 3, sum of two numbers, and product of these numbers must give us minus 4. So these numbers are minus 4 and 1. When we add minus 4 and 1, we get negative 3. When we multiply negative 4 and 1, we get negative 4. So we have k squared minus 4k plus k minus 4 equals to 0. K into k minus 4 plus 1 into k minus 4 equals to 0. Therefore, we have k plus 1, k minus 4 equals to 0. Therefore, k can either be equal to 4 or minus 1. Example 4. Show that y given by c1 sine 2x plus c2 cos 2x is a general solution to the differential equation given by y double prime plus 4y equals to 0. Now, in this differential equation, we have y and y double prime. Therefore, we are required to differentiate this solution twice. Let's start. Dy over dx. When we differentiate sine, we get positive cosine. But again, we need to differentiate this angle 2x with respect to x. We get 2. So that will be 2 c1 cos 2x. When we differentiate cosine, we get negative of sine. But again, we need to differentiate this angle 2x with respect to x. We get 2. So it becomes minus 2 c2 sine 2x. D squared y over dx squared gives us, when we differentiate cosine, we get negative of sine. But again, we need to differentiate this angle. So we have minus 4c1 sine 2x. When we differentiate sine, we get positive of cosine. Therefore, we have minus 4 c2 cos 2x. Now, since we have our y double prime and our y prime, we can make the substitution in this differential equation. So our y double prime is given by minus 4 c1 sine 2x minus 4 c2 cos 2x plus 4 into y. Y is our original equation given by c1 sine 2x plus c2 cos 2x. So we have minus 4 c1 sine 2x minus 4 c2 cos 2x plus 4 c1 sine 2x plus 4 c2 cos 2x, and this should be equal to 0. Minus 4 c1 sine 2x will cancel with plus 4 c1 sine 2x minus 4 c1 cos 2x, and this plus 4 c2 cos 2x will cancel, therefore giving us 0 equals to 0. Therefore, we have shown that the equation y equals to c1 sine 2x plus c2 cos 2x is indeed a solution to the differential equation given by y double prime plus 4y equals to 0. Now, the second part of this question says, determine a particular solution given y of 0 equals to 0 and y prime 0 equals to 1. Don't forget, this value represents x and this one represents y. Similarly, this one represents x and this represents y and this one represents x. So this one is an initial value problem. Now, y of x equals to c1 sine 2x plus c2 cos 2x. This is our original solution. Now, y of 0, we are substituting this first condition. Where there is x, we put 0, and where there is y, we also put 0. So this will give us c1 sine of 0 plus c2 cosine of 0. Now, we know that 0 equals to sine of 0 is 0. Therefore, this term will reduce to 0 and cosine of 0 is 1. So we have c2 equals to 0. Now, let's use this condition, y prime of 0. Now, we have that equation. It was given by 2c1 cos 0 minus 2c2 sine of 0. Now, we know that cosine of 0 is 1. So we have, in this equation, we have 1 equals to cosine of 0 is 1. So we have 2c1 and sine of 0 is 0. So all this will reduce to 0. Therefore, our c1 will be equal to a half. Since we have c1 as a half and c2 as 0, we can substitute them in our initial solution to get our particular solution. So we have y equals to c1 is a half sine 2x and c2 is 0. Therefore, the second part will reduce to 0. And this is our particular solution. Thank you for watching.